So I'm not going to pick up where I left off, because I think I left off doing like number 21, I think was the last one I did, but I'm going to start doing some trig sub ones. So like number 40, where should I start? 40, 39? Is that the first problem that I assigned you? Out of the homework, out of the textbook? 39?
Problems were 1 through 27 out and 39 through 60.
Yeah, 39 through 60 something. So let's do that. All right. Come on, Kiki. Again, here we go. Do y'all have that cheat sheet thing I gave y'all? The one? Yeah. Oh, you know what? You want one of these? Yeah, this is a new one. This is a different one. Okay. All right, so I'm doing number 39. I'm going to make sure I have this written down right. So just to be clear, out of the homework, out of the book, I told you to do what? 1 through? But the ones before that, 1 through what? 1 through 27. So I still have a couple to do there. I haven't done those yet. All right, who cares? I'll come back to those if I have time. 39, integral dx on top, but I like to always peel my dx off the side. The book always puts dx on top, and I think they do that to save room so they don't have to go as wide, or just to give you some variation. So we look at that, and what are you thinking? I mean, it's obvious because we know what section we're in, right? But what are you thinking? See the square root there? You've got a number minus something squared, your variable squared, which fits into. So this, according to this, we should make a substitution. I'm using the format that looks like this. Square root, what is my constant squared first, then minus my variable squared. So according to this, I should make the substitution x is equal to a sine theta, which for us in our problem, what's a? A is 2, right? So a for us is 2, right? 2 squared, and that means our x substitution is going to be 2 sine theta. So what do you do once you have that? Once you know what your substitution is going to be, remember there were 3 things now you go get? We'll figure out what the root is. Let's do the derivative first. Okay, so let's take the derivative of this first. The derivative of this is 2 cosine theta d theta, right, Zach? And now I have to get the root part, right? So I need to rewrite this root. And this is the part that some people were getting stuck on in class. Okay. This is equal to the square root of 4 minus what? If we rewrite x, so it's 2 sine theta, but squared, right? So what happens? You get 4 sine squared theta. And then what can you do here? Take a 4 out. Okay with that, Zach? And then what is this? Cosine squared theta. So this is equal to square root of 4 cosine squared theta. And that's what makes the trig substitution so good, is because you wind up at the end taking that complicated expression and rewriting it as a pretty simple trig expression. Right? 2 cosine theta. And so these are the 3 things. So I think I numbered them in class. 1, 2, and then 3. This equals this. And then you go and you just rewrite the whole problem. So let's go ahead and rewrite it. Any questions? All right. Integral. All right. 1, I'll do that part. 1 over. Do y'all care if I ask you? No? Zach? So the x squared is actually going to be what instead of 2 sine theta, but then squared. So that's what? 4 sine squared theta. Good. So that's what x squared is. Times 2 cosine theta, because that's what the root is. And don't ever forget dx, which is 2 cosine theta. D theta. Yeah. And some things actually happen pretty good here. But that cancels completely, and the 2, right? And so I have a 4 on the bottom that I can take out of the integral as a 1/4. The integral, I've got 1 over sine squared theta d theta. That's all, right? Any ideas on what to do with that? Good that you're thinking that, except for the fact that the sine squared is in a denominator. If it was on top, I totally agree. That's what we would do. But because it's in the denominator, can't really get away with that. Because it'll split it into 2 terms, but then you can't split it into 2 fractions, because 2 on the bottom, 1 on the top. Makes sense? It would actually probably make it a little bit worse.
So what have you compared it to the Pythagorean?
Like 1 minus cosine?
Yeah.
You could do that. I think you're going to be in the same boat, though, because
It'll be negative, you can bring the negative out, and it'll be 1 over cosine, which would just be secant.
you would have 1 minus cosine theta here, right?
Bottom.
2 terms, though. So that, again, you'd be stuck with that 1. What is 1 over sine theta? Cosecant? So isn't this cosecant squared? And now just go back and think about this for a second. Wasn't,
Formula 9.
yeah. Wasn't there something in Cal 1, the derivative of tangent was secant squared, the derivative of cotangent was negative cosecant squared. So going backwards, the antiderivative of this should be negative cotangent theta. But then we have a 1/4. So this is straight up, what formula did you say it was?
Formula number 9.
Formula number 9. There we go. Now we have to go back to x.
Reference triangles once you get back to x.
Yeah. Now reference triangles. So now I'm going to come over here, and I'm going to write down the information I have that connects x and theta together, which is always going to be your first substitution, the one that you got from the very beginning, which was x was 2 sine theta, right? Wasn't that it? Yeah, I'm pretty sure it's what we put. Yeah, it is. And then divide by 2 on both sides to create the ratio, and then draw your triangle based on this. A lot of times you'll see when I do these problems, a lot of times I draw my triangle even if I don't even need it. Like even if the problem doesn't require it, just to keep practicing this over and over and over. So which sides get labeled here? Two's the hypotenuse, opposite, and then that forces this side to be the square root, 4 minus x squared. And remember also I said that one of the sides will always be that square root thing that you had. All right. What is the definition of cotangent? It's the reciprocal of, so it's cosine over sine? Or adjacent over opposite, right? Adjacent over opposite. So this is going to become negative 1/4 times the adjacent side of this triangle over the opposite side. So root 4 minus x squared over the opposite side x plus some constant of integration. That's it. All right. We satisfied with that, or want to check it, or satisfied?
Check it since it's the first one.
You want to check it?
Since it's the first.
Okay, since it's the first one, we'll check it. All right. Okay, so I need to be able to take the derivative of this, right? So let's just not even deal with the negative 1/4 for right now. Let's just come back to that. Let's take derivative of this. So I have square root 4 minus x squared over x. I'm going to take its derivative, which means I'm going to use the quotient rule. The derivative of the top comes first. The derivative of the square root of something is 1 over 2 times the square root of that something. But because there's something inside of it, I have to do chain rule, which means derivative of the inside, which is negative 2x. That's the derivative of the top. Times the bottom, then minus the derivative of the bottom, which is 1, times the top, which is this. All of this over the bottom squared. And now at this point, I'm going to clean up the numerator. All right, so I have the negative 2, or the 2 here cancel. X times x is x squared. I have a negative. So I have negative x squared over root 4 minus x squared minus root 4 minus x squared. All of this over x. Not yet, they don't cancel because there's subtraction. If it was multiplication, yes. But I would have to put these together with a common denominator. Like if I want to combine these two together, so imagine that that's over 1, I would then have to multiply this top and bottom by what? Square root 4 minus x squared over square root 4 minus x squared. Now they would have the same denominator. So what I get is I have the negative x squared, which is this. This root times this root, the roots go away, and you just get 4 minus x squared. But it's subtraction. So it's actually minus 4 plus x squared. All over, oh, wait, hold on. This right here, x, was supposed to be squared, right? Sorry. All over the common denominator, which is this. All over what? X squared. These x squareds cancel, right? Or they add and they're gone. So then I have negative 4 over square root 4 minus x squared, all over still what? X squared, and I can look at x squared as being x squared over 1, and then flip it, and when I flip it I can put it in the back or the front. I'll just put it in the front here as x squared, and then a 1 up here, but I don't need that 1, right? I don't need to write the 1 up there, which is this. And then what was that constant I said to forget about? We'll just bring it in at the end. Okay. It was negative 1/4, wasn't it? So if you multiply this times negative 1/4, the negative and negative become positive, and then the 4 goes away, and you just have 1 over x squared root 4 minus x squared, which is the original problem, the original integrand. So it works, it checks out. Cool. All right. So I said 39 through what? Odds or no?
61 odd.
Odd, okay, I guess I'll just do the odds then. All right, 41. Square root x squared minus 4 over x dx. So you're thinking trig sub here again? What format do we have here for this? X squared minus a squared. We have the format square root x squared minus a squared, which according to this, I need to make the substitution x is equal to a secant theta. A for us in this problem would be what? 2. And so I'm going to make a substitution, x is equal to 2 secant theta. If I do this, things should all work out real nice. All right, so let's write down the 3 things that I said we'll need. X is 2 secant theta. Dx would be next, right? That'll be 2, and then the derivative of secant theta, which is secant theta tangent theta d theta. And then the square root thing we need to write, which I didn't write down what it is, but I think it's obvious what it is, right? It's the x squared minus 4. Square root of x squared minus 4 will be square root of, let's see, you want to do this one, Kiki?
4 secant squared theta
4 secant squared theta
minus 4.
minus 4, and that's using this, just squaring that.
And you take the 4 out and it becomes secant squared minus 1, which equals tangent squared.
Yep, this is,
4 tangent squared. Once you take it out of the root, then it's 2 tangent theta.
okay, good. So taking out the 4, you're left with this. That's a Pythagorean identity. That is tangent squared theta. And then square root of each one, you get 2 tan theta. 2 tan theta. So using that information, we should be able to rewrite the entire integral. And then at that point, it's a trig integral, and we try and do whatever. And do you see why we studied sine and cosine ones first, and then we studied tangent and secant ones next? See, this substitution requires secants and tangents, so we need to be able to handle this once it's all written out again. You know what I'm saying or not? I mean, we didn't deal with integrals that have like sine and cosecant in it. Like, why not? Because of the trig substitutions, the ones that you get at the end are usually sine and cosine or secants and tangents. So those are the 2 types we spent a lot of time on.
Sine and cosecant, you still break down into sine and cosine.
You could.
Yes, you could do that.
You could. We just like when it's secant and tangent, we like to use the fact that the derivatives of those are connected to each other. So,
Parallels, but not parallels anymore.
yeah. All right, so what's the numerator going to be? 2 tan theta over 2 secant theta. And then 2 secant theta tangent theta d theta. You see how important this dx is? I mean, we have to convert it to what it is, right? Which kind of created a little bit of an issue for us, but we should be able to handle this now. Secants cancel, 2's cancel. The 2 that's left can come out. Integral, then what? Tan squared theta. Is that all right like that? And then how do we integrate tan squared? Pythagorean identity? What do you mean?
Tan squared theta is secant squared minus 1.
Secant squared minus 1. Good. And you would rather deal with that one? Why would you rather deal with that? That's right. Exactly, because you know the antiderivative of this and you know the antiderivative of 1. Perfect. Good. All right. So, Kiki, you with us? Okay. So let's go ahead and take the antiderivatives now. We have 2, and then antiderivative of secant squared theta is just tangent theta. And the antiderivative of 1 is theta in this problem, because theta is the variable we're integrating with respect to. And that's our answer. But we need to get it back to x now, don't we? Was it x? I'm going to distribute the 2. I didn't have to. I don't know why. I just didn't like it sitting out there all lonely. reference triangle, I don't even know if I'll need it. I'm going to draw it anyway. So the information that I had was that x was 2 secant theta, right? X was 2 secant theta, which meant that x over 2 was secant theta, which meant if I draw a triangle, secant is the reciprocal of cosine, isn't it? So what side is which here?
X is on the hypotenuse and 2 is on the adjacent.
X is hypotenuse, 2 is adjacent. Do you agree? And that forces this other side to be this squared minus this squared, which better matched that root that you had earlier, which is, that's the root that started this whole thing off, right? All right, so we need tangent, right? We need tangent of theta over here. So 2 times tangent of theta is opposite over adjacent. So root x squared minus 4 over 2, that's nice. And then minus 2 times, theta. So how are you going to get theta? Where?
Where x is equal, since you're going back to x.
Okay, we can use this, or we can use this. Which one is going to be the one that we can get theta isolated from? Because you can't divide just SEC, those letters, right? You can't just divide that out. Arc, it would be the inverse secant function. So you're going to do arc secant or inverse secant on both sides. So if I take inverse secant on the left side, and I do inverse secant on the right side, it just gives me theta. And so that's what theta is. In terms of x, that's what it is. So that's what I put here. Secant inverse x over 2 plus c. We studied, in the very beginning, we studied the inverse trig functions and their derivatives. So if you go to your derivative formulas, you should have the derivative of that. Oh, hold on a second. Oh yeah, I was just saying that if we wanted to check this, which I'm not going to, you could look up the derivative of secant inverse, which is on there, and so we would have a way of differentiating that if we had to. These two's cancel. So, all right. Catching on to this? Yeah?
Yeah. I think I missed last time in this lecture.
You missed this lecture? Yeah.
Threw me off
Yeah.
completely.
What's the only answer to the ones that have trig in the answer? Everything else
That's right. Yep. And that's always going to happen if one of your things at the end here is theta. Just theta. Then when you go back to get x, you're going to have to use a trig function, an inverse trig function to get it back.
So in the answer, would you want it just left as is, or do you want the numerical value?
No, well, we don't know it because we don't know what x is,
Okay.
right? So we wouldn't be able to. No. All right, 43. Integral 1. This looks very similar to one we just did. T cubed square root t squared minus 1. Oh, no, it's not similar, is it? It's similar to 39. We had x squared, but then inside we had, I think, 4 minus x squared. Here it's a different, we're going to use a different substitution. And it's cubed here, not x squared. So what's the, let's see if we can do the actual substitution without having to write all that stuff down. Just say, what is the substitution going to be?
A would be square root of that.
A is the square root of 1, which is 1, right? So A is 1 here. So what substitution are we going to use according to this?
1 secant.
1 secant theta, right? 1 secant theta. So we're using the fact that we have the square root of the variable squared minus a constant squared. Now keep in mind, in the formula they use x, right? Here it's t. So we're not going to say x equals. We're going to say t equals. T equals 1 secant theta.
Which number is this for?
This is 43, yeah. Thanks. And then from here we differentiate. dt equals secant theta tangent theta. d theta. And then the square root part of this, t squared minus 1 equals, since we just did this, yeah, it's going to be just tangent theta, right? If you go through it. If I replace this with secant theta, secant squared theta minus 1 is exactly tangent squared theta and then square root. So tan theta. Is that all right, everyone? If you look on that formula sheet that I gave last semester, don't I tell you what the square root is? Yes, I do. I'm not telling them. Yeah. I'm going to tell them today. I'm going to allow them to add it to their formula sheet, but I wanted them to at least try some of the homework where they had to get this every single time.
So I believe you allowed us to add this along with the formula sheet.
Yeah.
I don't know about this.
Yeah, I don't know either. I don't really like this group that I've got. I'm kidding. Right, Kiki?
You're only saying that because you're on camera.
Did I turn my thing back on? Yeah. All right. Rewrite everything, right? 1 over secant cubed theta times tangent theta times
Secant tangent.
secant tangent. Okay, so
We'll leave you with 1 over secant squared.
1 over secant squared. Okay, I think you might finally get your wish here, Kiki.
What wish is that?
What you wanted to do earlier that you weren't able to do.
Which problem?
You'll see.
Cancel the bottom out.
Is that right?
Secant squared.
You're gonna have 1 over
1
secant
over
squared.
And then it's going to be 1 over 1. No.
What is secant square? What is secant? Sorry, what is 1 over secant the same as?
Cosine.
Cosine. So everyone's good with that, right? Okay. So this is really just 1 over secant's the same as cosine. So this is just cosine squared. You see what I'm saying now, Kiki? That's cosine squared theta. And now you can use that half angle or power reducing formula, whatever you want to call it. How many of you like that formula being called the half angle formula? I think that's what it's on the sheet, right? Isn't that what it says?
Reducing.
I'm talking about the one that's formula that says cosine squared x equals 1/2 times 1 plus cosine 2x. They call it half angle. I've never liked this being called the half angle identity. I don't know why, but I've never liked it.
Do you have a better one for it?
Power reducing. Because where is the half angle of that name coming
It's
from
because
here?
there's a half there, I'm pretty sure. Someone's like, let's just call it that.
Half angle, though, would to me imply half the angle. So what? Yeah. So I see. I understand why they're doing it, because here you have twice the angle, right? And in this side of the equation, it's half of that. So this is a way to relate this together, where you have double the angle or half the angle, half of that. But to me, this formula allows you to reduce the power. That, to me, is the key. You reduce the power from square down to linear. Yes, you double the angle in the process. But halving, I don't know, I just don't like it. So I'm going to continue to call it power reducing. And I didn't make that up. Some books, they do refer to it as the power reducing formula. So rewriting cosine squared theta as 1/2 times 1 plus cosine 2 theta, doubling that angle.
Just take the 1/2 out.
Take the 1/2 out, and then we'll be ready to integrate, won't we? So the 1/2's coming out. Integral of 1 plus cosine 2 theta d theta I could do integration all day long. I could just do this for 8 hours straight. Like that. Clock in, do integrals for 8 hours, clock out.
You already do.
Yeah, but not for 8 hours. I'm just saying I could if I had. I would enjoy that.
3 hours, 205 hours of lecture, you sure?
You know, I haven't lately. Now it's starting to be more like that. But okay, so what's my antiderivative here now?
1/2 theta plus 1/2 sine 2 theta.
Okay, so Zach, as soon as you see that theta, you're already thinking what?
That I have to remember to swap out theta after the reference triangle.
Yeah, so you're going to have some trig stuff. You noticed that, right? Or who said that?
You did.
Yeah, but I thought you were the one who pointed it out. Like you're always going to have a trig. Yeah, okay, that was the first one. Well, now that we see that, we know we're going to have a trig, an inverse trig in our answer somewhere. And then the antiderivative, be careful on this one. The antiderivative of cosine 2 theta is 1/2 sine 2 theta, right? Because you always have to scale out the a here.
Is that the 1/8?
That's the 1 over a right there. And then the 1/2 I'm just keeping out here. When it distributes through, it'll become a 1/4,
Okay.
right? 1/2 theta plus 1/4 sine 2 theta plus c. Now, again, because it's just in my nature to want to draw the reference triangle, I'm going to do that. I think I'll put it up here. We had t, right, not x. T was equal to secant theta. And that means that I can draw it right now, can't I? Remember, t is like t over 1. That's create your fraction that way because you don't have a number to divide through by. Secant's the reciprocal of cosine. So hypotenuse is t. Adjacent's 1. Opposite square root t squared minus 1.
And then shouldn't you get your, shouldn't you go ahead and get your theta?
Yeah, you want to get theta now? Sure, I'll get it right here. Secant inverse t equals theta. So take the arc secant on both sides, or inverse secant. That's right, noon. What about this though? We can't use that triangle on this. Why? It's 2 theta. You can only use, this triangle only works for trig functions of theta, not of 2 theta. But, what do we know about sine 2 theta?
Isn't that just sine theta, cosine theta?
2 sine theta, cosine theta, yes, correct. So going back, the pre-cal formula, this is called the double angle identity.
Do you not like that one either?
No, that one makes sense to me. Because it is a formula that involves the double angle, right? If this just so happened to be cosine of 2 theta, would you still be able to do something like this? Not exactly, but is there a formula for cosine 2 theta? There is. It's in the double angle identities. There's actually 3 equivalent versions of it,
Tangent.
right? And tangent, right? So you can handle any double angle. Now, what if this was a triple? You're stuck. You'd be stuck. You'd be stuck. But that would never happen because the way we got 2 theta was using the power reducing formula, which always doubles your angle. So you would never get a triple in there, if that makes
So
sense.
if it was 4, you have it squared.
Yeah. If this was 4, then what?
No.
This would, let's just answer that. If this was 4, then this would be 2 sine 2 theta cosine 2 theta. Then you do it again. Then you do each of those down. One more. That's not going to happen. But all right, so here we get, hey, we got our 1/2 back. Didn't we? All right, so where are we at? Let's get an answer up here. We have 1/2 theta. Theta was secant inverse of t. And then we have 1/2 again, plus, now, all this information. Sine theta, going off my triangle, that's just root t squared minus 1 over t times cosine theta, which is 1 over t, plus a constant. And I'll clean it up a little bit. Not much, but a little bit. So, I just don't like the 2 t's down here like that. I'm just going to put them together. So 1/2 arcsecant t plus root t squared minus 1 over 2t squared plus c. Box it, that's your answer. All right, 1207. I think we need to do something harder. 45, perfect. It's like it knew I was asking.
I
Yes.
was going to ask you, I think was on the trig integrals, there was a question that was like 5 sine of 2x and cosine of 5x. And I didn't know what it was.
Oh, okay. Yeah. Let me address that. It was. Do you have it with you or no? Yeah. This is one of those ones that's in the internet class that didn't find its way into the face-to-face class.
Yeah, it's sine 2x, cosine 5x. And it's just a constant, so it's going to be the remember.
That? Okay, so in your trig formulas, you have your formula sheets there, trig formulas? Let me see that. In the, where is it? I don't see it here. Well, that's not going to help. There's some formulas from pre-cal that are not on here because they're not used very often. It's the sum to product, product to sum formulas. So you might want to jot that down. And let me reference the page in the book. That way you'll know where to look for this. We haven't dealt with this before because we have different things inside, right? Like different arguments, 2x and 5x. So
It said
sum to product, product to sum formulas. Man, I don't know where it's going to be in here. I don't have them memorized. I just know that that's what we need. So let me see here. It might be Google time. Oh, nope, here they are. Okay, so it's an appendix. It's on A6, and it says this. Sine x cosine y equals 1/2 bracket sine x plus y plus sine x minus y, close brackets. This is what we would call a product to sum formula from pre-cal. And the great thing about it is that if you have two trig functions, sine and cosine, being multiplied, then you can split it up and it turns out to be two sine functions with addition, which means you can integrate these individually, which will be easy because it's just sine. So for us, what's x in this formula for us here? 2x, and y is actually 5x. So this integral, the new integral, becomes what? 1/2, which I'll just pull out. And then sine of x plus y. So add these two together, 2x plus 5x. So sine 7x plus, and then that one is x minus y. So that would be for us what? Sine of negative 3x dx. Does that make sense? And then at this point we integrate each of these. And so the antiderivative of sine is negative cosine, but then you have to scale by the a, then you have to hit it with the 1/2. So negative 1/14 cosine 7x. I'm going to erase this. This all right, or y'all following this? So this is 1/2 times negative 1/7 cosine 7x. So antiderivative of that is negative cosine, but then scale by the 7. This one over here is, again, negative cosine, but you scale by what this time? Negative 1/3. So you're going to have positive 1/2 times 1/3 cosine 3x plus c. So negative 1/14 cosine 7x.
And cosine 3x, you take out the negative?
The antiderivative of sine is negative cosine, but then we scale by negative 1/3. Negative and negative became plus.
Isn't there supposed
I
to be
mean, the
a
argument inside of cosine.
Oh, I forgot that. Well, I got lucky, actually. It wouldn't have mattered because cosine's an even function. So cosine of x is equal to cosine of negative x. But I did not intentionally do that. It's supposed to be negative. But it would have been, still would have been correct. All right. Thanks for bringing that up. All right, let's look at,
Real quick.
yeah,
Why is the 1/7 negative?
because the antiderivative of sine is negative cosine,
Oh, okay.
right?
Gotcha.
This next one is really the first problem that we've looked at, and we didn't look at this in class either. It's what we're going to start with today. It's a problem where things just aren't so obvious. So integral dx on top,
Is 45?
45, yes, thank you. A squared plus x squared to the 3/2 dx. That's it. That's the problem. So we assume here that a is a constant that we don't know what it is. All right. Normally they just gave us a number like 4 or 9 or 1 or something. They've been real nice and they've given us a number. Not this time.
Isn't there a way to split that up?
Well, I don't know what you mean by that, but you can't do this to that power, that to that power. You can't do that.
And she put it
Isn't
under
that
the
just mean to cube root?
What is that? What? I'm hearing two different things.
Kind of like what he said, can she put it under radical, so cube root?
Is that cube root though? So if you have this, this is x to the n over m. So when you do rational exponents, if you have a fraction up here as a power, the numerator is the power, the denominator is the root.
So it's square root of,
That's right. So this is really the square root of a squared plus x squared but then cubed, right? Cubed. You can actually put the cubed on the outside. So what I should say is that this right here is true, but this is also the same as the nth root of x then to the n. So this n power can come, you can do the nth power first, then take the cube root, or you can, or cube root, sorry. You can do the nth power of x first, then take the mth root, or you can do the nth root of x first and then take the nth power. The order of that does not matter. I'll give you an example. If you have cube root of 8 squared, right? What's 8 squared?
8 to the 2/3.
Yes, but I'm saying, we know that this is 8 to the 2/3, yes, but
64.
you could go cube root of 64, right? What's the cube root of 64? So what times itself 3 times gives you 64? 4 times 4 times 4? 4 times 4 times 4? So the answer here is 4, is that right? All agree? But I could also have done it this way, cube root of 8 and then squared the answer. So instead of squaring it and getting 64 first, I could have taken the cube root of 8 first, which would have been, it's a cube root of 8. 2, and then square it. 2, and then square it, and you get the same answer. So that's what I'm saying here, is that when you had this, I could have put the cubed in here like this, or I could have just cubed the whole root when I'm done. I'm choosing to do it this way. Why is it, do you think I would do that?
If you threw it in there,
It would be a lot more complicated.
Work with what's in there and then do with the cube.
That's right. What is this? What technique are we going to use for this here? The trig substitution. So we already know that when we do trig substitution, we wind up finding those 3 things, right? Whatever the substitution is, the derivative of it, and then the square root part. The square root part has always turned out to be something very nice, right? All we're going to have is that very nice thing cubed. That's all that's going to happen. So let's do this substitution. What do you do if you have your number squared and then your variable squared? What's the substitution we make?
Isn't that one also interchangeable?
What?
I guess x squared plus a squared.
The second one here? Yeah, it doesn't matter which way it is. X squared plus a squared or a squared plus x squared, you use the same substitution.
A tangent.
A tangent theta. And in this case, a is what? A is a. We don't know what it is. So a is tangent theta. And then derivative of that is a secant squared theta d theta. And then the square root part of this. A squared plus x squared is a squared plus a squared tan theta, tan squared theta. Right. So you're squaring x. What can you factor out of both of those? A squared. You're left with 1 plus tangent squared theta. And 1 plus tangent squared theta is really secant squared theta. And that's just a secant theta. So you see now the difference, like when someone gives you what it turns out to be versus understanding where it comes from a little bit. I think it's a little better to know. Okay. It's more practice with algebra too, so it's,
Kind of made one of the first examples because it doesn't show you any constants, it just gives you.
yeah. Yeah, so really you could say that anytime you make this substitution, right, this will always be your result, regardless of A. Right. All right, so you ready to rewrite this? Kiki, are we good?
Is that one squared and was not?
It was, this is this.
Okay, yeah, sorry, I was looking at one of those.
All right, I would like to rewrite this integral, and I'm going to I'm going to rewrite it from this version right here. Integral 1 over a secant theta, right? That's this. A secant theta is this. But then what? Cubed. Dx. Dx is a secant squared theta d theta. Oh, that's nice. We got lucky. We got real lucky there. You see why?
Because it basically becomes cosine.
Yep, that's going to become cosine. So let's see.
We took the A out of there since it's constant? Or do we-
Yeah, we're going to take the a out, and we're going to have to make sure we get the right number of a's here. Let's see. We have equals. I'm going to write one more line. I'm going to cube the bottom. You have to cube the a and the secant. Ah. All right. So we get the secant squared to cancel out completely here with two of the factors. That leaves you with just one secant on the bottom. And then you have this a cancels here, and you get a squared when you're done. So we'll pull 1 over a squared out. 1 over a squared integral of 1 over secant theta d theta. 1 over secant is cosine, right? So 1 over a squared integral cosine theta d theta. Zach, are you good? All right. And that one, antiderivative cosine, it's about as clean as it ever gets, right? You don't even have to worry about the sign, the positive, negative, or anything like that. And that's it, right? Triangle. A triangle comes off the substitution that I made. That was x equals a tan theta, which means x over a is equal to tangent theta. X over a is tan theta, which means that this side is x squared plus a squared, square root. And we need what? Sine? So sine is opposite over hypotenuse. There we go.
Since there's a square root on the bottom, do we, like in pre-cal, we were told to push that up? Do we have to do that, or can we just let that be?
Push what up?
Like
Oh
basically-
yeah, no. You just leave it.
Cool.
What was the question?
Rationalize the denominator, make that where the root's not down here. So you'd multiply top and bottom by this root. You don't need to do that. Let me check on what's going on at my house here. We're having carpet installed, and I had to leave the guys there.
I think your mic's still on.
That's all right.
We're just like, I'll edit that out later.
He looks confused. How's it going, man?
How you doing, sir?
Pretty good. Yourself?
What's that?
Yourself?
Pretty good.
Pretty good. What are you up to this semester?
Calcium.
Are you doing this online too?
Yeah, no, not online.
Face to face?
Yes, with
With who?
not sure his name is Alex, maybe?
Okay. Yeah. How's it going?
One okay.
Yeah. All right. Do we continue or what? Where are y'all at in your class?
The same thing. Sir.
Same thing? Okay. $47. Y'all want to try 47 yourself first? I'll put it up here.
Yeah.
And then I'll take a quick little break. I got to run to my office and get a couple of things for class. Got to print out that real big, there's a 5-question quiz that I'm going to be giving. I'm kidding. I'm kidding. No quiz. We don't have time for a quiz today. X squared plus 16 dx. So see what you can do with that. And if anyone